So last but not least, we have the biggest group, so biggest expectation. Yes, we also have Marcin that missed some bits about the location of these final events, but yeah, we are here on time. Pay attention for the, yes, probably it's for the beer. So who is the first one?
Good morning. So my group was involved on a very big data set, the GetItalia Dataset. This is also the company which I work for. And then the team, our team, there is Marcin, is from Poland, and is a very very experienced developer. Is a very advanced and skilled geek. There is Matteo, is from Pisa, Istituto Ricerca Sant'Anna, and Istituto Scuola Ricerca Sant'Anna, and he's a researcher, and he's our Python expert and very skilled on network science. And Pierre is from Val d'Aosta. He's working from for the region, and is managing a lot of data and exchanges great data set between Italian regions. And there is me. I work as a IT engineer. I'm mainly a developer. I'm a Java developer. Okay, the agenda. So what we should do with this data, and the presentation is organized with a first overview with the dataset, and then the next steps were about make this data to have some structure, and then make them more accurate, and then we started some processing, and we tried to represent some pattern and some other interesting visualizations. Okay, overview about data. As I said, data is about GPS tracking, is from GPS tracking system, and mainly the company installs on trucks GPS devices, and then provides to transportation companies web application and other security services to control the truck routes, and then make the fleet manager able to monitor the entire fleet and their tasks. There is also other features like security services and so on. About our idea was a very huge brainstorming for us, and then there are only some ideas like the research of patterns and more knowledge about drivers habits and their main jobs. Then about using data to find out if there are good places to, for example, open new gas stations, and then other ideas about, for example, track pooling to check if there are some possibilities to make different companies to share tracks, and for example go to with the track full and avoid the return to the original point with the track empty. Okay, the dataset is very huge. Is coming from a SATTRACK platform that, as I said, collects many data, mainly tracking data. The company is monitoring about 10,000 vehicles, mainly in Italy and Western Europe. Tracking data, I mean GPS coordinates and other additional data is the main and the core dataset. But there are also many different kind of data, but the volumes are really less huge. We was involved on the dataset about May 2014, and there was about 6 gigabytes of data. Okay, this is a very basic description on the dataset structure. So this is the main dataset, and we add, for example, vehicle ID anonymized, and the timestamp of the sample, latitude, longitude, the current speed, the status of the engine, and then other additional data like the trigger that is related to the sample, and many other fields. For example, the total odometer that we discovered is not very it's very accurate, and so on. Okay, and we also played with additional data like fuel consumption data that is was available only for a portion of the vehicles. About we had 4 million records about consumptions. That was enough to make some hypothesis analysis about gas stations. And then we had also vehicle grouping by client, so we can add the information about the company fleets. Okay.
Okay, so the first thing that we started doing was actually to try to clean the dataset and to use it in a proper way, because as you have seen before from this actual snapshot, this is just one of the files that we had, and it was 1 million entries. So the point was that we had 44, 45 files like this, so we couldn't work with all of them simultaneously, so we needed to parse them and reduce the dimension in some way or another. So first of all, we started by saying, okay, let's keep only the records for the triggers that were related to a driver turning on or off the truck. So we removed all the middle samples that were taking maybe after some kilometers or after some time. So we removed all of that. We kept only the ones that were related to truck is on, truck is off. Then what we said, okay, but anyway, since we had data mostly for Italy, but actually also from some parts of Northern Europe and so on, we said, okay, let's try to stick with Italy since we have the highest density of points. So the first, let's say, rough cleaning that we did was to basically throw away all the points or the coordinates that were outside the bounding box of Italy. So that was just the first screening to drop many data points. And then what we did was to remove also all the tracks that didn't have the information about the travel distance, because as Carlo was saying, we don't only have the coordinates. We can of course compute over the coordinates the geodesic distance between the two coordinates, but we actually had also the odometer distance, which was measured basically looking at the actual geodesic distance, but at the different sampling points. So in principle, that distance should have been more precise with respect to simply using a straight line from one location to another. But of course, that that information was not available for all the trucks, for all the vehicles. So we just removed all the vehicles that didn't have that measure. And then the second step was to actually check whether or not the accuracy of the GPS was good enough for us, because we had coordinates up to the 6th digital point, but we actually discovered that probably we could stop at the 3rd one, and this would come handy afterwards. And so we basically grouped our data in limiting it to the 3rd decimal point. And then the other idea was to basically, and this is still a kind of work in progress, to, let's say, clean from our dataset, purge from our dataset all those tracks that had, let's say, misplaced coordinates. Because what could happen is that maybe the device is recording the actual coordinate, then it cannot send the signal, then it will send it at some point in the future, but maybe it will arrive at a different time compared to the most recent one, and so on. So basically, you can have tracks jumping around. So what we were trying to do desperately yesterday was to try to complete also this step. We didn't manage, but we partially did it. So the first task that we had to do once we, let's say, reduced the size of the dataset was to actually reverse geocode our coordinates, because having just 2 numbers for latitude and longitude was not telling us anything. I mean, at least eyeballing it to know where where the track actually was. So what we wanted to do was, okay, let's use Google Maps API or Google OpenStreetMap APIs, and let's just give them the coordinates and get back the location, the actual name of the location of the track. Unfortunately, this cannot work in our case because we had too many points, so the number of requests that we would have been allowed to use were not enough. So we disregarded this option quickly, and then we moved to the second one. The second one came from finding this resource, geonames.org. And from there, basically, we had a list of tuples with location and zip codes. And for each such tuple, we had also information of what should have been the centroid for that geographical area. So then what we said was, okay, let's basically get this data and let's just try to compute the geodesic distance between this data point and the ones that we have in our dataset. And let's assign each track to the geographical area whose centroid is the nearest one. Unfortunately, the first pass that we did on this couldn't possibly work in a reasonable time because we were thinking about doing it brute force, so to check all the cross pairs, and of course, we wouldn't have enough time to do it. So then we said, okay, let's try to use this KD3 space partitioning data structure. So the idea here is basically, and sorry for the computer scientists in the room, I'm not a computer scientist, so I'll do my best. The idea is basically if you have data with high dimensionality, you basically try to group them in a tree, and you try to keep the points which are close to each other in this n-dimensional space in the same, let's say, branch of the tree. So the idea is that with this algorithm that was already implemented, fortunately in Cython, but within scikit-learn, we were able basically to speed up all this matching of the distances, because basically what we will do is you set a length of leaves that you want to have, and basically the algorithm will just go on brute force checking all the cross coordinates only after going through a certain part of the tree. So the first part is fast, and then only let's say the fine tuning is run in the brute force mode. And doing it this way, we were able to speed up a lot our computations. But of course, there is an additional problem that, okay, we are using centroids, but maybe doing this way, we are misclassifying still the coordinates, because maybe we are assigning, in case of maybe neighboring regions or weirdly shaped regions and so on, you can assign maybe the track to a different geographical area, administrative geographical area than the one that you actually wanted to. So we said, okay, probably we have to find a third approach. And the third approach was to say, okay, let's simply use shapefiles. And the idea is this is an example for provinces. Basically, we have this kind of data for regions, provinces, and cities. The idea is that for each administrative area, you had actually the boundaries of the region. So the idea is, instead of simply check the distance between our point, and the centroid of the area, simply check if the point is within the area. So we did that, but of course here the problem is that we couldn't implement fastly the KD3 here, because doing it from scratch probably wouldn't have had enough time. And of course doing this in pure Python was painful and too slow, so what we resulted in doing was to use C++ and use the Boost geometry library, because in that there was already a function to actually perform this kind of operation. And doing this we were able to do it in I think in a almost less than 2 hours on all our data. And then once we had that, what we wanted to do is actually extract the trajectories and then basically the path that were traveled by the different tracks. So what we ended up with is something like this. Is a table where you have the source location, the destination, and for the source you have both the name of the actual place. You cannot see it here, but you can see it here, because you will have source region, which will mean the name of the region, the name of the province, the name of the town from where the truck was coming. The same for the target, for the destination. Also an ISTAT code for that geographical area. Since here we're not working with actually zip codes, but with the ISTAT codes with something slightly different. And then again the coordinates. This distance is the one that is computed looking at the odometer parameter that we had in our data set. Then we have the time passed in seconds between between the movement from one location to the destination location. And then geodistance, which is basically the hover sign distance between the two coordinates. Once we did that, we said, okay, first of all, maybe we want to try to compute some statistics for the different areas, because then our idea was to plot this in a nice way in a map. So what we did was to simply count, let's say roughly, the number of unique trucks stopping in each given location, the cumulative time spent stopping there, and the average time spent in that specific location. In this case, by stops, I mean that basically we filtered out all those source destinations combinations where we actually could infer that the truck was not moving, or maybe was just moving some meters but not actually traveling. So for doing these statistics, we compute the actual stops that the trucks made. And then we also said, okay, let's try to have a graph representation of this. So the idea is that the nodes will actually be the administrative geographical areas that we are selecting, which will be region, provinces, or cities. The edges will be, of course, the trajectory of the truck moving from one place to the other one, from one node to the next one, and the weight will simply be the rough count of how many trucks traveled along that trajectory. And yes, let's see if I can zoom in. Maybe not. Okay, this was just simply an example of a small part of the graph. And then what we said, okay, let's try to see, since the initial idea, very long-term idea, will be to see if truck pooling will make sense for given the data that we have, was, okay, let's first try to see if we can group trajectories together. That is, can we say that there is a sort of natural clustering between the pattern followed by different trucks? Let's say, can we say that, trucks that are in a specific area can maybe are sticking around in that area and so on, so we can actually partition our map according to different regions that are behaving in a sense in a similar way within the region. And what we decided to do was to use InfoMap for this. And the underlying idea is, okay, where is it? Okay, here you cannot see it well. Okay, but basically because there is no the start button. Okay, but the idea is you have a graph and you have a random walker that is walking around, jumping around this graph, and you actually want to record where this person moving is. In order to do it, basically you need to attach IDs to the different nodes, right? The rough way to do it will be to have a unique ID for each node, but that of course is not efficient, because if you have communities, what will happen is that a person will start to jump around, and maybe it will stick more within this cluster, and then it will go out because there is a higher density of edges here instead of the edges of the density that there is maybe between those two groups of nodes. So what will happen will be that maybe the person will start jumping here, then it will stay here for a bit, go out, go in, and so on. So it's not efficient to give actually unique IDs for each node. What is more efficient is to find the smart partitioning And then what you do is give unique IDs for the nodes only within the cluster, and then give basically just an ID that tells you, okay, this guy is moving from this cluster to this one. So in that way, you reduce the length of the string that is recording the movements of your walker. And given that we were dealing with tracks in a special place and so on, we decided, okay, maybe this could work and actually have a nice explanation and a nice flavor to it. Okay, now. Okay, so the first thing that we tried was to do this with the geonames data. That is with the data when we were actually looking at the distance only between our coordinates and the centroids. And this is the map that resulted from that. And this, as you see, is at this is at actually the town zip code level, so it's very fine-grained. Then we moved to actually the one with the regions, and this is, well, you can't see anything, but okay, at least you can see the colors. Of course, the coloring gives you the community of the nodes. So these nodes will stick together. These nodes are in the same community. Again, these nodes and these three nodes. And then we did, of course, the same. We went on and we said, okay, let's do it for provinces. And here you can see Italy even better. Here it's even better. Okay, in this case, there were 5 communities. And then we did it for actually each individual city, and this is the resulting map. Actually, those are just I'm plotting only the communities that had at least 1% of the points in the dataset, because otherwise you couldn't see really anything from here. So this is just, I mean, the smallest one were filtered out, let's say. Okay. And then we move to the gas station part.
Well, we got plenty of key off events. That it's when the truck turned the key off, and we wanted, with using that data, to map the gas stations in at least in Italy. So we wanted to have to cluster all the stops, all the near stops in a single spot, to have a bunch of points we could compare with a real list of points of interest that's saying the gas stations taken from other sources of data. Yeah, well, clustering turned out to be very tricky to do. We have a very large data set, so we have some computing problems. And my main problem, at least, was with the data is noisy. So we have to work with a non-perfect data set, which is, I think, a normal case. But we, at least in some fields, we hadn't the possibility to clean the data. We had to work with dirty data, and that was our problem. I ran many that MapReduce jobs that simply crashed because of I couldn't expect what the data in a single point in a big database was saying to me. So yeah. Okay, we wanted to classify stop events based on metadata on stops from the database. So we wanted to know if a precise stop was a refueling event. So comparing the data on stops with the data on fuel levels. And we wanted to end up with a map of a gas station and popularity of the gas station from the truck drivers. Okay, so the problem was that doing that clustering was very hard because of debugging Hadoop is tedious. So knowing what the problem really was in a precise processing is something I still have to discover how to do. Okay, visualization.
Yeah, do we have a demo?
Yeah, sure.
Okay, so what I'm going to show right now is was 2 things in one. It was first an attempt to take a look at all the data we've got, which is 45 million rows, and second is it was supposed to be a basis for further visualization. So this is the data. Quite a lot of it. On top of that, we have a layer of gas stations, 30-something thousand.
and also a layer of administrative zones Matteo mentioned. This is the town level, I think. And further, our idea was to actually compute some statistics on this level for gas stations and for individual zones, but we ran out of time. Now, the problem with this visualization was, of course, that this is a lot of data. And after a couple of approaches, what we ended up doing was first sampling the data. What you see here is not 45 million data, it's 1% of the data, which is still way more than enough for a visualization like that. Even if you zoom in really, you have to go very close to note that there are actually breaks and gaps in the data. So the stack here, software stack was on top. There is that's leaflet showing tiles generated using Mapnik via the tile mill interface, which is a very nice application until you throw more than 500,000 points at it. Then it starts having trouble communicating with itself, saying that tile mill server has gone away quite a lot. Other than that, a bunch of the usual JavaScript libraries like underscore, jQuery, D3.js. As I said, the plan was to show statistics. We unfortunately don't have those statistics right now because we ran out of time. So that was the demo. Okay, so problems and difficulties. As I said, that's quite a lot of data. A couple of problems, like writing data analysis algorithms in Python turned out to be a very bad idea, which is where pandas and NumPy and occasional code in C++ really helps. Multiprocessing pool is awesome. Cython, yes. Wormholes. We, as Matteo mentioned, we had a lot of problems with data not being as perfect as we'd like it to be. Not even close in some cases, where we've got light speed trucks moving across the country. So in retrospect, what would most likely help would be to first get some idea of the data, of the kind of problems there are, pre-process the data, then sample it, and then do something meaningful with it. Because otherwise there is so much noise, it makes things difficult. And also, I think, as you mentioned, sloppy code really causes a lot of time waste. Final remarks, we had a pretty different set of skills. Unfortunately, no designer which shows on the visualization part. Project was very nice in that we had from the start a pretty chaotic vision of what we wanted to do, like something to do with this kind of data and that kind of data, which cost us quite a lot of time, I think. On the other hand, that was a chance to play with quite a lot of data, and that's very useful. Yeah, and Big Dive, for all of us, ended up being a great training and a chance to actually start using the libraries like Pandas and NumPy and graph processing and generating ties from a lot of data, which was very useful, and I think we will come up useful in further projects. So, thanks.
Let me ask an extra round of applause for these guys that really worked a lot.